Okay, imagine this. 74,000 years ago, Sumatra. The Earth just rips open.
An explosion unlike almost anything humans have ever witnessed.
Exactly. Welcome to our deep dive on the Toba supereruption. We're looking at the eruption itself, this idea of a volcanic winter, and whether it nearly, ended us.
Right, the genetic bottleneck theory. It's a fascinating and pretty controversial topic.
Totally. Your sources cover the sheer power, the science behind that potential global chill, the arguments for and against a human catastrophe.
And really, the story of how our ancestors managed to pull through.
So our mission today, let's unpack the Toba enigma, figure out what it really meant for early humans.
Okay, first off, the scale. Toba was immense. We classify these things using the Volcanic Explosivity Index, or VEI.
And that's like the Richter scale, right?
Logarithmic.
Precisely. Each whole number jump means a 10-fold increase in the ejected material. Mount St. Helens in 1980, a VEI 5.
Okay.
Krakatoa, Tambora bigger, VEI 6 and 7. Toba was a VEI 8.
Wow, so orders of magnitude larger. We're talking maybe 2,800, possibly over 5,300 cubic kilometers of rock and ash ejected. It's just mind-bogglingly vast compared to historical eruptions.
And this happened in Sumatra, creating that huge lake we see today, Lake Toba.
That's the one. The lake fills the caldera, the collapsed area left after the eruption.
So immediate devastation must have been incredible, pyroclastic flows.
Oh, absolutely. Superheated, fast-moving clouds of gas and debris, anything in their path, just gone. Hundreds of degrees moving at hurricane speeds.
And the ash didn't just stay there, did it?
Not at all. That's a key point. Toba ash layers are found across India, the Arabian Sea, Bay of Bengal, maybe even traces in Africa.
So it's like a geological fingerprint, a time marker.
Exactly, an isochron. But, and this is crucial for the global story, the ash itself wasn't the main driver of potential global climate change.
Right. That was the gas, wasn't it? The sulfur?
Yes, sulfur dioxide, SO2, blasted way up into the stratosphere, much higher than normal clouds.
And up.
It reacts with water to form tiny droplets, aerosols of sulfuric acid, and those can hang around for years.
Okay, and they block sunlight.
They scatter sunlight back into space, basically. Less sun reaching the surface means cooling, the volcanic winter scenario.
Which could mess with rainfall, growing seasons, everything.
Potentially, yes. The initial hypothesis, based on the eruption size, was for a really severe winter, maybe 3 to 15 degrees Celsius drop globally.
15 degrees. That's Ice Age territory. For how long?
Some early models suggested 6, maybe 10 years, or even longer, a devastating impact on ecosystems worldwide.
But it's more complicated now, isn't it? That initial picture is being challenged.
It is. Climate modeling is complex. For one thing, if you get too many aerosols, they can clump together, get bigger, and fall out of the sky faster. They also become less efficient at scattering light.
Ah, okay. Self-limiting, sort of.
Kind of. Plus, SO2 itself absorbs some radiation, and you have other gases like halogens involved. It's not just a simple sunscreen effect.
And the evidence on the ground? Does it match a massive long winter?
That's where it gets really interesting. Ice cores give conflicting signals, and crucially, sediment cores from Lake Malawi in East Africa don't show a major ecosystem crash or cooling event around 74,000 years ago.
Huh. And humans in India?
Archaeological sites in India, like in the Juru Valley, show people living there right through the Toba ash layer, using the same kinds of tools before and after. No sign of a total collapse.
So the newer climate models suggest what? Less extreme cooling?
Generally, yes. Maybe more like 1.5 to 3.5 degrees Celsius cooling, and perhaps for a shorter time. Still significant, but maybe not the global cataclysm first envisioned.
Okay, this brings us right to the human bottleneck idea. We know humans have relatively low genetic diversity compared to, say, chimps.
Right, which suggests our ancestors went through a period where their population size drastically reduced. A bottleneck.
And the Toba catastrophe theory, proposed by Stanley Ambrose back in '98, linked this directly to that severe volcanic winter.
Exactly. The narrative was, Toba erupts, triggers a brutal winter, ecosystems collapse globally, humans starve, and only a tiny number survive, maybe just a few thousand breeding pairs.
A real near-extinction event. Dark skies, failing rains, animals dying off. A desperate struggle.
That was the compelling and, frankly, terrifying picture painted.
But the archaeology we just mentioned, in India and Africa, It doesn't quite fit that, does it?
It doesn't seem to. The continuity in India is a big challenge to the idea of a global human population crash caused by Toba, and no sign of it in Lake Malawi's ecosystem. We also don't see Neanderthals suddenly blinking out then either.
And the genetics.
Hmm.
Has the timing of the bottleneck been reevaluated too?
Yes. More recent genetic studies point to the major bottleneck for non-African populations happening later, maybe around 50,000 to 60,000 years ago.
Coinciding more with the main out-of-Africa migration.
Precisely. The idea is that the small group or groups that migrated out of Africa carried only a fraction of the total human genetic diversity with them. That's the founder effect.
So the low diversity outside Africa might be more about who left Africa, rather than a global die-off from Toba.
That's the prevailing view now, yes. And there's even evidence for earlier population dips within Africa long before Toba.
Okay, so Toba probably wasn't the event that almost wiped humanity out.
Likely not, but that doesn't mean it wasn't a massive environmental shock.
Absolutely. So instead of near extinction, what does Toba tell us about our ancestors? It must have tested them severely.
Immensely. It shifts the focus to resilience and adaptability. How did different groups cope? Maybe their location mattered, their specific environment.
Technology, too. Flexibility.
For sure. Being able to adapt hunting or gathering strategies, maybe having better tools,
Right.
cognitive flexibility, problem solving.
And maybe social networks, cooperation, helping each other through lean times.
That's a strong possibility. Ambrose himself suggested Toba might have selected for greater cooperation. Facing such a challenge might have reinforced the need for strong social bonds.
So Toba becomes less about a brush with death and more a story about surviving a profound test.
Exactly. A testament to human resilience in the face of incredible environmental pressure.
What are the big takeaways then?
Well, one, the sheer power of Earth's geological forces. Two, how difficult it is to piece together deep history and how science corrects itself with new evidence.
Yeah, the story keeps evolving.
And three, understanding these past events helps us model risks today, whether from future supervolcanoes or ongoing climate change.
So wrapping up, Toba. A monster eruption, no doubt. Its climate impact. Probably significant, but maybe not the apocalyptic winter first proposed. The human bottleneck. Now looking more linked to migrations out of Africa.
And the enduring message is one of resilience. Our ancestors faced this colossal challenge, adapted and survived, allowing us to be here today.
It really makes you think. Here's something to ponder. Forget 74,000 years ago. If a Toba-scale event, or even a less dramatic but still global environmental shock, happened today, how would our modern interconnected world cope? Would our technology save us, or would our interconnectedness be our downfall?